mics up over there.
So I'm a senior fellow at AMD Research in Austin. I drove here this morning in my own car. They recommend we normally take a rental car for this trip, but there are no rental cars available in Austin this week. Thanks to something known as South by Southwest, or as the local residents refer to it, a good time to get out of town. So here I am. So this has been a good year for AMD. We've announced new processors. Ryzen is the code name for our client systems. EPYC is the server version of that. We are selling our GPUs as fast as we can make them, thanks in large part to cryptocurrency mining. And I personally have been involved in the DOE Path Forward research projects for exascale system. That picture there is of the Titan system at Oak Ridge. It's still the fastest US-based system on the top 500. It's made with AMD processors and NVIDIA GPUs. Because we're expanding and growing, I also want to mention we are hiring. My management requires that, really in terms of hardware, software, especially expertise in HPC or machine intelligence. Please see me afterwards. We'll give you more information about that in my business card. We did announce our new Zen Core in our Ryzen systems, but I also want to mention that we have significant enhancements on that already flowing through the development pipeline, coming out on a regular cadence in the near future. Same thing for our GPUs, including a quick shift to 7 nanometer technology throughout the next couple years. In particular, our next GPU will be a Ryzen 7 nanometer system with enhancements for both HPC and machine intelligence operations on there. Now, those of you who work in the industry can imagine how many hoops I had to jump through to get approval to just announce such a vague hardware roadmap, forward-looking directions. But we did manage that, completed about 2 hours ago. And I'll set that aside and actually go into some technical discussions now. So heterogeneous computing has been a big buzzword for a while. IEEE Micro did a whole special edition on it a while ago, editorial on that about heterogeneous computing being a response to the power wall. AMD actually had an article in there about achieving exascale capabilities through heterogeneous computing. We did an update on that, HPC conference in January 2017. Green computing, top 500 also makes very extensive use. Almost everyone is using accelerators there. And why is that? So many of you have a feeling of what's going on here, but I like this little illustration to show what's happening. If you think of general purpose cores, their performance per watt is reasonably good over a fairly wide application space. But if you look at application specific cores, such as general purpose GPUs, they can get much better power performance. In some cases, people are saying 2x to 10x improvements in performance per watt, but over a much more limited set of applications. And if you take that one step further with specialized accelerator logic, you can get even higher improvements in performance per watt, but again, over even a more limited range of applications. There are two kind of humorous anecdotes people come up with in the industry. One is that we can actually build an exascale system today, no problem. You can build it, you just can't turn it on. It's going to be over 100 megawatts of power. And that's not strictly true, because the other anecdote is you can actually build an exascale system today that fits well within the large data center power requirements. You just can't run any of your programs on it because it's built completely with special purpose accelerators. So the trick is how to design the special purpose accelerators and the GPUs and the interconnect and the software support so they can be widely used going forward. I'm going to skip over this chart quickly. There's a bunch of reasons why people tried accelerators in the past. They didn't work out too well, but a lot of things are changing in terms of Dennard scaling ending, silicon getting a lot cheaper, standards becoming more stable, and so on. So the ecosystem for accelerators is improving greatly. Here's another example. It shows accelerators actually very widely used in very high commodity parts. This is a Snapdragon chip for cell phones, and just gives an illustration there of all the different types of specialized hardware accelerators to put on there to get really high performance at really good power efficiency. So this is recognized well within the industry. Besides heterogeneous in computing, it's also in memory. On the left, you see the HBM module, new type of very high bandwidth stacked memory. AMD has been shipping this since June 2015. We're the first person to ship this in volume. NVIDIA, Intel have joined us now. The industry has moved over to HBM version 2. HBM3 is now on the JEDEC planning committee. And on the right, you see the 3D crosspoint, kind of a storage class memory, much faster than flash, but not good enough to replace DRAM yet. So this is one example. This is going to be a whole lot of these types of storage class memories coming down the development pipeline in the next couple years. And this leads to a heterogeneous memory system, some very fast, limited capacity memory, regular DRAM DIMMs, and then various ranges of storage class memory. How do you manage all this from a software point of view? And that is an unsolved problem right now. I just want to point out two DOE labs showing some innovation here. Two projects doing research on this, Unity and SICM from various DOE labs. You can find out more information about this on the web if you're interested. Let me go back a second and introduce this. Besides technology, you also need interfaces to the new technology. And right now we have DDR and HBM interfaces, which are serving the industry very well, but they're very highly tuned to DRAM technology. They're not well suited for all the new technologies coming down the pipeline. You also have PCIe, which has been very good to the industry, but it has its limitations for accelerators. And we're heading towards an area where you're going to have accelerator cards that have lots of memory on them, or alternatively, memory modules that have lots of computation on them. So you really need a new interface, and there's a lot of open standard efforts to develop that. Now I'll mention what I think are the three big ones here: Gen Z, CCIX, or C6 as some people call it, and OpenCAPI, all from different companies. AMD is a strong believer in open standards, so we're actually on the board of all three of these, pushing them forward. I personally think, one, you're going to hear a lot more about that the next 2 days here, and two is when these things start being well supported, it has the potential for opening up a whole new wave of innovation in the industry in terms of what type of memory modules, what type of accelerators, what type of combination memory and accelerators you can hook up to systems. So stay tuned for some interesting developments in this area. I think it's very promising. Besides the interconnect technology, there is the software support. And again, this is an unsolved problem. One area we're putting a lot of emphasis on is the heterogeneous system architecture, HSA. Again, it's an open standard programming model. Large number of companies and national labs are involved in this. Basically, it is an accelerator model that includes shared virtual memory that is coherent, plus user space, user queues to dispatch work without having to go through the operating system, do that very efficiently. You can check out a lot more information on that on the web. This is a really interesting open standard programming model. And we have a open standard implementation of this we call ROCm, Radeon Open Compute Platform. And the key modules are one we call HIP. And you can kind of, at a high level, think of this as an open standards alternative to CUDA. and it includes ways to translate from CUDA to this open standard. There's HCC, which is really a single source C++ language that allows you to also target GPU accelerators. And then, of course, there's OpenCL, which has been around for quite a while. These are all open standards available on the web now, regularly updating them. We're also working on development of a couple of new additional things. You'll probably hear more about OpenMP before the conference is over. DOE is very interested in this as a way to handle programming for a large range of heterogeneous systems, highly parallel systems. OpenMP 5 is being developed now. That'll include a lot of cases for heterogeneous memory and so on. These are really big, complicated standards, and AMD is working in collaboration with other groups to develop support for them. Beyond OpenMP, there's a whole bunch of other things in, I'll say, the research stage. We've been looking at Chapel, Legion, OpenSHMEM, libfabric, and so on, that are all being developed. They have not caught on quite as well yet. Above and beyond the basic ROCm software support, we are also working on a great deal of support for machine intelligence. OpenMI here, or MI Open, is basically an open source alternative to CUDNN. This, along with the base ROCm support I mentioned earlier, plus all the libraries for hardware, math operations, and so on, are being supported. We also support a number of the common industry frameworks for machine intelligence, Caffe, TensorFlow, Torch 7, with Caffe 2 and MXNet coming out real soon now. And again, this is all open standard. It's freely available to the public. And I want to wrap up by saying it's not just GPUs and CPUs. A true heterogeneous system has things like FPGAs involved in it. And in fact, I was the co-author of this white paper that we released jointly with Xilinx at Supercomputing last year. You can find it on the web, probably best by just searching for the name. Unified Deep Learning with CPU, GPU, and FPGA technologies. Basically, it outlines some of the cases and benefits of architecting systems with CPUs and GPUs and FPGA for a combination of deep learning training, inference, and large data analytics all at the same time on real-time systems. Again, stay tuned for more developments there. And finally, I just want to wrap up and say AMD is here to stay at high performance. We've been working on heterogeneous systems for many years now, and we're really pushing this hard in terms of both the technologies, the open standards, and the software support to make it happen.
So it's a good bit of time where you can ask some questions. And so I'll actually start off. So you talk about all the different softwares and the standardizations and software frameworks and whatnot. So how do we affect change on a very short time scale? Because some of these things tend to take an incredible amount of time to really find its way into it when it just kind of meanders through the standards committee and whatnot. So sometimes, how do you bootstrap that and get it in use? And what's your thoughts about that?
I'm not sure I have a good answer for that. We are certainly open to collaboration, working with the universities, the Open Standards Committee, and the national labs. Yeah. And we're open to other collaboration also. Because it's open standard, we can push it out fairly quickly and get regular updates. Okay. That's the best I can tell you for now.
Any other questions? No questions? No questions? Oh, there's one in the back. Let me get you to the microphone.
Thank you for the talk. So you mentioned that there is heterogeneity in memory that is coming up in the next few years. How would you comment on programmers' work with regard to that? Is it going to be a burden on the programmer to take care of managing all those heterogeneity in memory, or would you think that that will be taken care of by software?
So there's a simple answer to that, and then there's the more complex performance tuning answer. For some of these, you can actually manage some of the levels of memory by using it as a hardware cache. And Intel provides some of that with their HBM stacks. At higher levels of memory, storage class of memory and so on, you can actually do managed paging, either by hardware or the operating system can intervene to move pages around for you to wherever they will be best used to maximize performance. And we're doing a lot of work on optimizing for that too. But so both of those techniques can be used without necessarily having to modify programs. There's a lot of work on providing program support, though, for actually tuning the performance. OpenMP will have some of that. There's a lot of other work. Linux has support for NUMA operations that are being advanced that allow you to specifically place things in specific locations and help allocate memory and put the data processing close to that memory. So there's plenty of research work on there, plenty of new developments coming on how you optimize performance. But that's still an open problem in the long run. And once you actually get a lot more of this heterogeneous memory systems on there, I expect graduate students and so on will be doing a lot of work to help solve this problem for us.
Anybody else? So graduate students, get ready.
Yeah.
It's a Raspberry Pi of the hardware. Okay. If there is none, then we'll let us thank Mike again. Yeah.